All right, so after curve sketching, one of the applications that we look at is physics for the calculus and vectors. So this lesson will specifically be targeting concepts regarding physics. If you didn't take any physics, for shame, absolute for shame that you didn't take the physics. I don't feel sorry for you at all. But anyway, if you didn't take it, you will be just fine with this component of the unit because it's just looking at a process or how to deal with the algebraic component with the physics concepts. So today, what's the goal? I can apply my knowledge and understanding of derivatives, and I want you to apply them to real-world situations, and we're keying in on velocity and acceleration. So you need to sketch some distance time graphs, and for the people that are that have taken the physics, be glad we're not talking face-to-face here because I'd be putting you on the spot and asking you some questions from last year's physics courses. So we have two types of motion, and I'll just make that line a little bit better. We have uniform motion, which means that you're moving at a steady pace. So in grade 9, you did an exercise with the graphing calculators, and you determined that if it was a line, it was a constant pace, which meant that the velocity time graph, the velocity, because you're moving at a uniform pace, then you're walking with a uniform speed. So how do you determine that uniform speed? Well, remember, this is a measurement of distance. So let's say meters, and time is in seconds. And the whole concept with this in the grade 9 course was that slope, being rise over run, was equal to, in terms of units, rise is in meters, runs in seconds, it's meters per second, which is equal to a velocity. So if you found the slope, then the slope was your velocity. If you were moving at a constant speed, all right, if you were moving with a constant speed, that means you weren't accelerating at all. So that means if you look at the acceleration time graph, your acceleration would be 0. And that's the slope from your velocity time graph. All right, so m would equal 0, or I guess m2 in this case, we'll call that m1. All right. Where it got a little bit more complicated in the physics course was when you had non-uniform motion. With non-uniform motion, that meant your velocity was changing constantly. And the process we came up with was that we had to find the slope of a whole bunch of tangent lines to determine 3 points on the velocity time graph. Because remember, finding the slope from here is meters per second. So then we would plot, started at a velocity of 0, plot, 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 and we'd find that our velocity was increasing at a steady rate or a steady pace. Okay, so we'd find slope 1, slope 2, slope 3, and those values would be sketched in as such there. So by doing the tangent method, and then to find the acceleration time graph, or the acceleration for this particular scenario, again, you would find the slope here, rise over run, would be meters per second over meters, so you'd end up with a non-uniform motion, or that means you'd end up with an acceleration. So the whole concept here with the physics is that you were finding the slope to move from dt to vt to at. Okay, so this is what we summarized in the grade 11 physics specifically, was that if we wanted to find velocity from displacement, we would find slope. If I wanted to find acceleration from a velocity time graph, I would find slope. Well, now that we know derivatives, now with derivatives, we can find the slope from equations representing motion. Okay, so we can determine slope from displacement equations. So we don't need the graphs anymore. We don't need to find tangents anymore. We can go ahead and just find exactly that. We can find the slope. So this is for the people that took physics. So the people that didn't take physics, don't panic on this slide. Just kind of follow along. So hopefully people who took physics will recognize this as one of our physics formulas. If I take the derivative of displacement with respect to time, then we know that we'd be taking the derivative of t. So we would be left with v1, and then delta t, derivative of that would be 1, plus 0.5a. Derivative of delta t squared would be 2 delta t to the exponent 1. So my question is, what is the change in displacement with respect to time? It becomes velocity. So change in displacement with respect to time is velocity. And the right side just needs a little bit of cleaning up. 2 times a half is 1, a delta t. So most physics students should be saying, oh, that's cool. That's how you get from first calculus and first principles. That's how you would move from a displacement equation to one of our other kinematics equations. All right, so there we go. So there is the connection or a connection on, or the relationship between displacement and velocity. All right, the rest of us now. Looking at a couple of examples to go through. So now for the physics students, we no longer have graphs anymore. We're just looking at being given some algebraic equations to work with and manipulate. So the position of an object is given by that function. So I don't understand, I don't care for it. They use displacement or position with s of t. So the function for displacement is always s of t. And we want to answer the following. So what is the position after 4 seconds? So we want to know the displacement after 4 seconds. We're simply taking our displacement equation and substituting in the value. All right, so very, very complicated example to start with here. So -2 times 16 plus 8. So when we do that and simplify, we end up with -24 meters. So therefore, our displacement is 24 meters backwards. All right, it is a vector, so you do have to give a direction with the magnitude. B part. What is the instantaneous velocity after 4 seconds? So physics students right away are thinking, okay, we need to find the slope of the tangent. What is the slope of the tangent? Well, by definition, if you remember back to the definition that we talked about of a derivative, the derivative is, or represents, it's an expression that is the slope of the tangent line to a function. If we take the derivative of the function s of t with respect to t, we would end up with -4t. Well, the change in displacement with respect to time is velocity. It is instantaneous velocity. So v of t equals -4t. And the question wants us to know, what is the velocity at 4 seconds? So we're just substituting in 4. So it's -16 meters per second. So we end up with, therefore, the instantaneous velocity after 4 seconds is 16 meters per second, again, backwards because we have a negative value. All right. C part. C part is, what is the acceleration after 4 seconds? Well, if I know an expression for velocity, and velocity is -4t, then the change in velocity with respect to time, so I'm taking the derivative with respect to time, would be -4. And I know that this term is simply acceleration. Okay. And it is, in fact, a constant, so it doesn't matter the time here. So therefore, it could be after 7 seconds, 9 seconds. Basically, this object is accelerating backwards. So therefore, the acceleration acceleration is 4 meters per second squared backwards. And finally, D part, when is the object stationary? So basically we're asking, if we're asking when is the object stationary, when is the velocity equal to 0? That's what we're asking in this question. So 0 equals negative 4t. So the possibility then is that t equals 0 seconds. So at the start, t equals 0, velocity is 0 meters per second. There you go. So all you need to remember is the derivative of displacement or position is velocity. The derivative of velocity is acceleration. All right, next example. Actually, I'll finish the next example, the final example, up in the next video. That way I'm not so rushed.